Hey guys, this is our second video on kinematics and we're continuing our introduction with kinematics. This time we're going to have a bigger link with our calculus methods. So the scenario we're looking at is we're looking at the vertical displacement of a ball being thrown up in the air. And if you think of that, maybe you've got a ball in your hand right now, you lob it up and then it goes back down. So it looks a little bit like a negative parabola. And what would happen? Normally, this is where you start it. It gets thrown up, it goes down. And our x-axis, that is time. And the y-axis is normally a measure of distance. We're going to call it meters this time around. And the ball that we've been thrown, so our st, our function of s in terms of time will be 40t minus 5t squared. So that means at any point in time, however many seconds gone by, you'll be able to calculate the height of the ball at that particular time. So st, that relates to the distance or the displacement. So we can find out how high it is. So st 40t minus 5 squared. So what we can do is we can figure out, well, how high was it at the 0 second mark? That's another way of saying how high was it to start off with. So it'd be 40 times 0 minus 5 times 0 squared, and all of that comes to 0. And that makes sense because you haven't thrown the ball yet, so it hasn't been displaced, it hasn't gone up in any height. And then you could also maybe figure out, well, after 1 second, how high was that ball? And that would be 40 times 1 minus 5 times 1 squared. And that would be 40 minus 5. And that would be 35. And what that means is that ball would be 35 meters high after 1 second. And just a really important note, I didn't do it for the first two, but make sure you're including your units. Our displacement is often a measure of distance, and in our case, it is how high the ball is off the ground. So hopefully that makes sense. That's our first start. So what I'm going to do is I'm going to rub out our bottom bit of working. If you did miss that, make sure you pause it and get that down. So that's all gone. Let's change pen colors. So let's now start looking at the velocity. So the velocity is actually equal to the derivative of st. And in this case, that is going to be 40 minus 10t. So this is the rate of change. So think of a car. So your car can travel 300 kilometers. That's just the distance. But in the odometer in your car, you can actually see how fast you're traveling per hour. And that's what velocity is. So it's how fast something is actually traveling as opposed to how far something has traveled. So we've got our derivative. So let's try again. So initially, so you've just thrown it, you haven't quite released it. You can actually figure out how far or how fast it's going. So that would be 40 minus 10, which would be 40. So that means at the time of release, the ball would have been traveling 40 meters per second. And let's say, or maybe it's 2 seconds in, how fast would that be traveling? You would suggest once you've thrown the ball up, it should slow down with the effect of gravity. So let's say 40 minus 10 times 2. And that there is 20. Well, it's traveling at 20 meters per second. And again, that makes total sense. So let's say maybe after 4 seconds, how fast is it traveling? So that's 4 minus 10 times 4. That's 40 minus 40, which is 0 meters per second. And what that means at this point here is actually stopped accelerating. So it stopped moving. So maybe that's where the ball has hit the ground. So maybe it's taken 4 seconds to go from start to finish. And then finally, let's look at one last one. So what would the velocity be after 5 seconds? So at 4 seconds, we figured out, well, it's probably stopped because it's hit the ground. But what would happen at 5 seconds? So let's put that in. So that would be 40 minus 10 to the power 5. That's 40 minus 50, which is equal to negative 10 meters per second. So that's a bit of a weird number. That's kind of suggesting the ball's going backwards. But I think what that to me suggests is it's just a practical limitation of the scenario we're looking at, because by then the ball probably would have hit, which means anything below or anything with a negative distance in our context probably isn't relevant or practical. So that was a quick go at the velocity. So let's now have a look. We're going to clear our blue working. We're going to finish off with our acceleration, and let's explore that a little bit. So this time around, I'm pausing the video. So if you haven't got this down, please do. Okay, we're back. We're at our final step. We're now trying to find the acceleration of the ball at any particular point. So the acceleration in terms of time, that is going to be equal to the derivative of the velocity, which will be equal to the second derivative of the displacement. And in our case, that is simply negative 10. And in this case here, don't forget our units, that's meters per second squared. So what that means is at every point in our throw, the speed of the ball is reducing by 10 meters per second. And if you think about the practical context of that, you've just thrown a ball. At the point in time you've thrown the ball is probably traveling at its fastest. And as the ball travels through the air, drag and wind resistance slows that ball down to the point where it hits the ground and it stops. Hopefully you found this short video useful. So what we did is we explored the displacement, the velocity, and acceleration. We did focus on the differentiation side of things. We will have future lessons where we go backwards from the acceleration to the velocity and from the velocity to the displacement. Okay, let's get into heaps of practice now.